This video is going to be a relatively quick overview of ColourSpace, of the various options and capabilities that it presents to the user, and hopefully explain why it is so far advanced compared to any other calibration system, and obviously provides far superior calibration results and better colour management. When we open the first splash screen, we get presented with three different options, which are basically the ColourSpace Management Library, the profiling options, and the LUT tools options. As you can see, the windows are all free floating and you can move things around and do whatever you want at any given time. You can even open multiple windows of the same type, so you can have different libraries open to be looking at different parameters. So, the preset color spaces, the profiles of displays that have been profiled within the system, camera color spaces, the user modified camera color spaces, and so on. You can also open up multiple profiling windows so that you can be looking at one profile on one while performing a measurement on another. Let's just connect to the OEM probe to show that that connects. There we go. And if we were to go to the same probe on here, it will tell you that that probe is busy. So you can see you can mix and match as required. The same with, you could have multiple LUT windows open, so you could be assessing one LUT and maybe performing modifications on it in the way of, say, doing any of the maths tools or whatever, while assessing another one to see exactly what the parameters are that it presents. But if we go back to the beginning and start with the library space, looking at it in a little bit more detail, you have three presets, which are the color spaces that come inbuilt into ColourSpace, camera presets if you have cameras, and the profiles, which are just the three film stocks we use for doing things like look management to do emulation of film output. You then got the user spaces, so if you've modified a color space, you can then save it as a new alternate color space. So for example, you go, I don't know, sRGB, modify. If you wanted to change the gamma to a different value or something, call it a different name, save it, and then that will appear in the user spaces. Same with cameras, in that you can take a camera, red, modify, and you've got various parameters for the camera itself that you can modify and then save as a new preset, which will appear in the users. Again, means that you can generate look LUTs that are matched to the camera in question and to the target color space. And then we've got the actual profiles, which are the measurements of displays made using ColourSpace that are saved after profiling has completed. Again, they can be modified in different ways, because you can extract from them a color space, so you can match a display to itself, extract a profile for probe matching, or add augment data. Augment data means you could add, for example, a secondary profile to a first profile, with the secondary profile enhancing the accuracy of the first profile. Again, things that are pretty unique to ColourSpace. And if we call up a profile, let's look for the a large one. There we go, chroma, no probe match, 21 cube 3. Display that, and with that open, we can start to assess what's going on with the display. So initially, we have the various graph options that we can get into to look at the way that display is responding in the various parameters, all of which can be zoomed into and assessed for far greater detail, including drift. And if we move along the top here, you can see that we have first up the settings menu, where you can set the global parameters for the profiling window, connect to your probes and set the probe settings, connect to hardware, be they LUT boxes, displays, or patch generators. The graph options, so you can choose to do things like enable, disable the tangents, change the delta E mathematics, select to see, say, just grayscale or a grayscale and primary, secondary, everything, filter based on the errors, so we can look at, for example, just the orange errors in the profile, orange being between a delta of 1 and 2.3, because 2.3 is the JND. Obviously look at green and red, which is above 2.3, with green obviously being below 1. You can change the graph into a cube graph when you're in the volumetric graphs. This helps you to really understand what's going on. For example, with this display, we can see that it's not making the blue primary. The error looks worse than it is because this is a linear representation of what is effectively a logarithmic error, but it helps you to really understand what's going on with the display. And obviously back to the standard CIE graphs. And then we have the manual measure, so you can take manual measurements of any display either using the sliders to preset your colour patches, or using presets themselves, which are just CSV lists of particular colours, in this case grayscales followed by memory colours, and you can just click on those and take measurements or use Auto Advanced to step through them, as with a characterisation. Talking of which, characterisation, you have a number of preset standard characterisation patch sets, or again you can actually use any of your own generated patch sets rather than the ones that we provide automatically. And there we go, that's the custom. You've also got the ability to choose sequential or an isometric when you're doing cube-based processing, which is obviously defined by the size of the cube, the number of patches in its side, so 21 cube 3, which gives you just over 9,000 patches. You can use drift compensation, DIP mode if you're using something like Ted's fantastic light space disk for an external patch source. Obviously toggle patch color on and off, and all of that gives you a very high level of control over the profile information, both for recording it and assessing it. But we can take that further because we can open up a number of different graphs that give you enhanced information on what the display profile is showing you. So for example, here we're now looking at zoomed in versions of the CIE, looking at the red, green and blue primaries. We have a larger EOTF gamma curve. We've zoomed in on the grayscale. We have again a larger EOTF, the differential graph this time, and RGB balance. And all these graphs can be resized and positioned and zoomed into independently. And obviously we'll have things like the tangents visible, so you can start to see where errors are and what direction the error is occurring in. Now while we're looking at this graph, obviously we're not seeing a lot of useful information because it's just telling us there's a lot of error, and that's because we are looking at this profile against a Rec 709 color space. But the display itself was profiled while in wide gamut mode, as you can see by the amount of gamut that the display actually covers. So realistically, we want to get a feel for this by looking at it compared to its own gamut and gamma, and then we get a feel for the underlying potential of the display. So if we go back into our managed spaces and we take the chroma profile, we'll modify it, and we're going to use extract. So we'll just give that an extract name and use extract space. And now when we go into color spaces, there is our new color space, and that means that we can use that in our target color space drop down. And now we start to see more of the accuracy or not of the display. Now at the minute we're not quite right because it's defaulted back to 100 nits maximum and 0 nits minimum, whereas I want to use the actual min and max of the display. And now we are comparing both the gamma, gamut and luminance values to the display's native values. And that starts to give us a real feel for what this display can do when calibrated, because we can basically see it is very linear. It is tracking very nicely to its own raw gamut and gamma. And the errors, as we'd expect in an LCD display, are just down in the shadows, as we can see in the volumetric graph. And if we go back to our graph options and we look at just the errors that are above a delta E of 2.3, I mean, we can see there's an error there, which it looks like it's possibly just a random error reading. So we may want to take that out of the profile. And to do that, we can go to our top graph. And if we look at the tangents, you can see that the errors are all saturation. They are all tracking in towards the center point. Now note, they're not tracking towards white because they're in the low level area of the profile. As we can see volumetrically, they're all right down in the shadows. And that means that this display down in the shadows, the white point is offset towards blue because it has a blue backlight. And we can see that in the RGB balance graph, because that is exactly what this is telling us, that the display has got a blue backlight, that as the backlight gets brighter and brighter, gets less and less blue until it tracks into the correct white point. So, knowing that, we can actually use the information provided in the tangent lines to see that that point there is tracking differently. That suggests that that's the error point we can see in the volumetric graph. If I double click it, we get some information on it, but more importantly, back in the volumetric graph, we now have a cross on that error. So that means that, yeah, that is the point that appears to have been read incorrectly. And we can either reread that, because that is now selected in our manual measure graph. You can see that it's actually picked up the actual data of that point. If you look, for example, at the DE value there, it tells you that it is exactly the same as the DE value of the selected point there. That means we can now use either measure to remeasure if we have a probe connected. In fact, if we were to do that, we could actually connect to the I1D3, and you'll see that we can now remeasure that point and it will correct it if we were on that display. As it happens, we're not on that display at the moment. So rather than correct it, I'm just going to delete it. That way, ColourSpace will interpolate around that missing point and fill in that data when we generate a LUT. We don't have to have every point in the graph when we are generating a LUT, and often it can be better to not have a point rather than have a point with an error. So when it comes to measuring, we have the option of using manual measure or using characterization. Characterization will automatically profile based on the options that we choose as our profile source. So for example, if we were to do a cube with a small patch size of say 5 by 5, actually we'll do it bigger because we're going to abort it. So 12, there we go, gives us just over 1700 patches. We'll remove that graph and replace it with a patch window, and we'll just quickly put a probe on there so you get an idea. And we have our I1D3 connected with these parameters set. We don't need extra delay. We'll leave intelligent integration on, and basically we can tell it to measure any patch we want. So we could use the sliders to say set black. We will delete the existing points and start from scratch, and then measure. And you can see the green line telling us that it's taking a measurement. Because intelligent integration is on, it's taking a little longer, and it's now plotted the first point, which in this case is black, and we can see in the RGB balance that obviously there is, in this display, it actually has a red backlight compared to the previous one, which was a blue backlight. And then we could lock the sliders, do white and remeasure, and again you can see that compared to our target color space, we actually have a green-white error. But that's because we're still targeting the previous display's extracted color space. So we'll go to Rec 709 instead. There we go. So that brings things a little closer together. Obviously our min and max are not the same, so we can just update those. And we can carry on to do that. Now we could, for example, step through each grayscale in 10% steps. Just click above, measure, click above, measure, click above, measure. And you can see we are just building up a profile one point at a time. Obviously, if we were parked on one and were making manual adjustments, we can use repeat and measure, and it will now continuously measure that same point, and we can use the display's inbuilt color management controls to get the measured point as accurate as possible. When we stop, the last one will be saved into the profile, and we can just literally finish off that. Just why not? There we go. So we've now done that profile with the 10% steps throughout. We could use, rather than that, our presets, and these are just CSV lists, as we did earlier. So we can now use that to auto advance, and when we measure, it will now step through the entire list of patches one at a time, taking each measurement and plotting the data into the graph. It'll populate the CIE graphs as it goes, but it won't populate the grayscale because that's updated at the end. And it's actually adding into the existing graph that we just made. So if you look, you can see it's building up additional points into the grayscale, adding to those that we manually did earlier. Okay, we'll just abort that. As well as the manual measure, we have obviously the characterization. So if we go into Cube, we can select the size we require, either with a slider or just dial in a number. And then we could choose an isometric sequential. An isometric is the preferred for most situations because it averages out the power going to the display, prevents kind of thermal issues. We could use drift compensation so we can see how the display drifts. If we nip back into settings, we could actually have stabilization patches added. So we're adding a black in between each measured patch. It just helps to, again, deal with thermal issues. And then basically start that profile off. We're starting a new profile, that's good. It will now just step through all 9,447 patches and build up a profile. So as the profile is being built up, we can look at the information in different ways as well. Obviously the graphs are all interactive as they're built up. And in the manual measure, you can see that the sliders and the values are all set to each patch in turn. And you can actually see information on the measurements being taken. Now we don't want to just sit here and run all through that, so we'll abort at this point and look at an existing profile. So there we go, it's aborted, and the partial results have been retained. So should we want to look at them to see if there are any issues that we may want to assess before restarting the profile, it at least allows us to take that option, and we can save the profile if we wanted to assess it at our leisure a bit later. For now we will delete points. But now we have all of our data in the profile. We can open up a previous one. And obviously, if we use the same one as before, and we can obviously now use that to generate a LUT to our target colour space, be that Rec 709, DCI-P3, or one of the HDR standards if we're measured to that kind of luminance level. But in this instance, we're just going to use this to generate a LUT for the standard Rec 709. And if we now go into our LUT generation tools, and we just say we want a profile to Rec 709, we are going to use our 21 Cube 3 profile. And we can choose to use drift compensation because that has been built into the profile. If we look here, we can see there that there is drift profile data, albeit relatively stable, but there is nevertheless a little bit of drift going on in the display, probably through thermal activity. And if we wanted, we could obviously use things like hint and that, which are obviously more complicated. But we're basically just going to call this Rec 709 new, give it a name. We're going to use peak chroma out of the various options. I'm going to disable gamut mapping on this one to start with, and we're going to make a new LUT. Let's just say no G map and create. Here we go. the LUT has been created, and we can visualize it in our 3D cube space or as a 1D LUT. And we can see that there is obviously blue being pushed up against the edge of the cube here. That's because of that clipping that we saw when we were looking at the original profile. Just turn off the tangents. There we go. So because of that bit of clipping where the display cannot make that blue gamut, and that is what we are seeing here, where the points are being pushed up against the cube. There are two ways of dealing with that. One is to just allow the LUT to clip, which is what I'm doing now, or if we disable that tick box, so we have enabled gamut mapping, and if we recreate the LUT again, we can then look at the difference. Basically, gamut mapping has to apply some form of change to the data that is clipped so that all the points aren't the same, and that either means a change in hue, a change in saturation, or a change in luminance, or any combination of those three. There we go. And if we default the original LUT back and step between them, you can see a difference just in that area predominantly. And now that we've got our LUT, we may want to apply a filter to it. So into our LUT adjust, and if we choose filters, and let's say the relax filter. Now this is specifically going to be aimed at the low light area here, because you can see that in this LUT, because the display has a very blue backlight, the LUT is quite correctly taking it out, but that may cause an artifact in the absolute shadow details where we would prefer to see a little bit too much blue rather than have the blue channel almost clipping. It's getting to that point of being obviously pushed down quite low. There's no clipping, but it's being pushed very low. So what we may want to do is just say for the very lower portion of this, say up to about a 0.1, we're going to apply a relax filter. We're going to sync the sliders, and then we can say that the low will turn on at 0, because we want it to come on here, and then turn off at about 0.1. So off at about 0.1, again just roughly, and apply. And there you can see that now it has effectively just smoothed out what's happening in the shadows. Maybe that's too harsh. Maybe we would want to move that down to say a little lower to about 5.9 and apply. There we go. So you can see we can just play with it until we get a value that is giving us the type of LUT that we want. And there we go. And that is being saved into our Unity LUT here, sorry, into our LUT library here. In this case we're working on the no gamut map, so that LUT now has that modification applied to it. Once we've done that, we can move into our hardware options and choose a display or a LUT box or something to load that LUT into. In this case this is a profile for the ASUS display, so we will connect to the ASUS and we can select the LUT that we want to upload GMAP. There we go. And if I hit upload, it will then upload that LUT into this display. While we're looking at the LUT, before we move into any other areas, you've obviously got the image tools where we can actually see the LUT applied or not, so we can see the effect it's having on a set Granger. We can load in our own images and add different pictures to it. So if we go to our desktop and say contrast count, and again just see the LUT being applied in the highlights, we can export that as an image which adds the LUT data to the image we have selected here, so that we can again use it elsewhere in external programs or load it back into another ColourSpace system. And obviously we have a plethora of different tools built into the system for working with things like ASUS CDLs, for performing mathematical functions, for generating array looks, and more.